Hi everyone, Assalamualaikum and good morning. So for second international conference on advanced engineering and applied science ICAES 2024 for today, I would like to present my paper which is entitled Heat Transfer Characteristic of Vertical Cooling Using Synthetic Jet. My paper ID is 51 and my name is Hazimi bin Ismail. As technology continues to advance and devices become more compact and powerful, managing heat dissipation is becoming increasingly crucial. Excessive heat can cause electronic devices to experience thermal failure, ultimately leading to breakdowns. The growing cooling demands of modern electronic components are driving the development of newer cooling systems designed to either replace or improve existing ones. Okay, so there are so many innovations in the cooling technologies, but one such innovation is the use of synthetic jets. A synthetic jet is a fluidic device that generates a jet of air or other fluid without the need of external supply lines. It operates by using a diaphragm or membrane that moves back and forth within a cavity, drawing in fluid through an opening and then expelling it to create a high velocity jets. These jets are characterized by their ability to induce strong turbulence and mixing in the surrounding fluid, making them highly effective for applications such as cooling electronics components, enhancing heat transfer, and controlling airflow in aerodynamic systems. Synthetic jets are valued for their compactness, efficiency, and the ability to be precisely controlled. In recent studies, it was suggested that the type of equipment used to move the fluid, like a loudspeaker or piezoelectric transducer, is more important than the appearance of cavity fins. And other notable studies it also mentioned that the frequencies of synthetic jets ranging from 300 Hz to 700 Hz. It is observed that with a heater synthetic jet distance of 50 mm, it was determined that a frequency of 500 Hz resulted the most effective cooling effect. And another recent studies by the SM Firdaus and etc. The large vortex formation, fluid velocity, and amplitude of the synthetic jet working at the resonant frequency were all directly directed to the heat transfer coefficient. One potential configuration for synthetic jet cooling involves placing it vertically, which may result in distinct effect compared to other positions. The parameters used for synthetic jet cooling may differ from those used in other cooling devices, and they also have distinct optimum parameters that have been determined in this study. The synthetic jet diaphragm was integrated into the body of the tool using synthetic jet actuators. The tool was designed with an adjustable tube, allowing for variations in size to accommodate different liquid volumes. The nozzle of the tool could be adjusted between 2 mm and 10 mm in diameter, while the hollow depth ranged from 1 mm to 5 mm. To provide versatility in operation, 25 synthetic jet actuators were employed, each offering a unique combination of nozzle size and volume cavity. Various synthetic jet controllers, as shown in Figure 2, were utilized to manage these actuators. In the Figure 3 provides a visual representation of the tools using during the trial, detailing the assembly of the synthetic jet generators and the placement of the synthetic jet. The experiment was conducted in a vertical cooling position as depicted in Figure 4, with the distance between the heater and the synthetic jet, as well as nozzle size and volume, being key experimental variables. A comprehensive list of all tools involved in the project is presented in Table 1. The experiment commenced with the activation of the power source, which initiated the heating process. The temperature changes were monitored in real time on a computer screen using the data logger application. And it also connected to the data acquisition module, DAM. To achieve and maintain a temperature of 70 degrees Celsius, the voltage was adjusted to 3.5 volts and the current to 0.85 ampere. The heater was kept on for 15 minutes to stabilize the temperature. Subsequently, the generator was activated with a 10-volt power supply and a frequency of 500 Hz. A windshield was placed over the setup for 50 minutes before data collection began. This process was repeated with varying distance, nozzle size, and volume cavities. Each iteration of the experiment required the heater to reach a stable temperature of 70 degrees Celsius while maintaining voltage of 70 volts and 1 ampere current. The formula used to calculate the heat transfer coefficients is shown in the equation 1 in the slides. And after that, after we obtain the value of heat transfer coefficient H, we use the Nusselt number equation to calculate the Nusselt number. So we will compare the Nusselt number for configurations that we have done in this experiment. For diameter nozzle of 2 mm, we obtain 7.56 of Nusselt number, which obtained at 30 mm with a cavity depth of 1 mm. And for the nozzle with the 4 mm size, the Nusselt number is much higher, which is 13.83, also obtained at the 30 mm value of distance, and also the volume cavity depth of 1 mm. Okay. And for the 6 mm diameter size, the Nusselt number is 12.08. And for the 8 mm diameter size, the Nusselt number is 12.21. And for the distance to heat surface effects, we found that the Nusselt number is 15.04. And for the distance of 20 mm from the heat surface, we found that the Nusselt number, the highest Nusselt number we found is 14.66, that found in the 20 mm distance. And for the 40 mm distance, we get the Nusselt number of 15.08. And for the 50 mm distance from the heat surface to the our synthetic jet, we found that the Nusselt number, the highest Nusselt number is the 12.77. And for the details of the results and data, you can find in our articles. And for the trend that we found, it shows that the distance changes are small compared to the volume depth and volume depth variations effects. And for the volume cavity depth increases, the Nusselt numbers will decrease, similar to past studies. And the Nusselt number also will expand, but non-linearly with nozzle diameter in most cases. And finally, the pattern remains constant across every setting of distance to heat transfer, which is the optimum value is 30 mm. The investigation shows that the synthetic jet performed best for vertical cooling at 30 mm. The ideal volume cavity depth is 1 mm and nozzle diameter is 2 mm. 30 mm spacing provides the best cooling in all setups, regardless of nozzle diameter or cavity depth. As volume cavity depth increases, synthetic jet performance drop. Note that performance decreases more beyond 30 mm. For further additional research, attention might be directed into studying the variability in the shape of the volume cavity rather than limiting it to a cylinder as done in the study. A cone is one possible option for the shape of volume cavity. This can enhance the creation of a vortex generated by a synthetic jet. The synthetic jet is now positioned at 90-degree angle to the heater, resulting in vertical cooling. Hence, for the future research, we should prioritize investigating the impact of varying the angle between the synthetic jet and heater surface to get further insight into the influence of angle on synthetic jet performance. I would like to thank to Mechanical Engineering Studies, College of Engineering, University Technology Mara, Pulau Pinang branch, and also the Malaysian Higher Education Department that grant us for the research grants. And for the references, you can find it and also similar to our references in our article. Thank you. So for any question and answer, you can send me to this address, email, and we will try to answer and respond accordingly. Thank you and have a nice day.